right, number 55 on page 88 said, think of a function that has vertical asymptotes at x equals 6, x equals negative 2, and a 0 at x equals 3. Okay, this is one that you had to generate. Okay, so let's just figure it out. How do you get an asymptote at a specific number? How do you get one? How do you force one? Make the denominator 0 at that x value, right? Okay, so let's try to do that. So I'm going to generate it right here. So if I want to have an asymptote at x equals 6, then what I would do is I would make x minus 6 in the denominator. Okay? Alright, so that one's good. What if I want to also make an asymptote, vertical asymptote at x equals negative 2? X plus 2. Oops. See that? Okay. And then the third component is, how do I make a 0 at x equals 3? The only way a fraction is equal to 0 is if it's 0 in the top. So, if I put up here, I say x minus 3, okay, then we zoom in on this bugger. Would you look at that? Okay, so what do we got? We've got vertical asymptote at x equals negative 2 and at 6, and it's a 0 at x equals 3. Okay? This is one of those questions where it helps to not just be so rigid to only know how to do specific problems. This is the kind of problem that is good, that if you can answer this, that means you got a general picture of how things work, which is so much more important than just knowing specific problems. Okay, so that's how we can do that. Now obviously it said that's just what you had to have, but you could add to it if you wanted to. You could say, well, you know, what if I want to have another asymptote at 1? Okay, and then another asymptote at x minus 4. X equals 4. So you can make whatever you want to. Okay, it still has those, but it just has little extras. And then if you change this to some constant, then some slider, then you can add a slider and you can say what happens to this if A changes, okay, and then it gets all funky and weird and does some cool stuff. Okay, so these are all different functions that are being drawn one after the other with a different A value. But then it really gets fun if you do things like this. B and you add a slider, and then C and you add a slider. And then you just let those things go.
You're already using C.
Using C, so D, add a slider, and you just let all these things go. These are all of those different functions. Okay.
What AP Calc kids do in their free time?
That's right. It's all fun and games.
What free time?
Okay, moving on. Boyle's law was number 57, and it said Boyle's law. You guys remember this from science? Okay. Boyle's law says this: for a quantity of gas at a constant temperature, the pressure is inversely proportional to the volume.
That's 58.
That's
58.
You didn't have to do 58?
No, 57.
That
You had to do
number is
58.
58.
Oh, thank you. There.
Oh, okay.
That was the one that was on my board, on my sheet. 58. So the quantity of gas is at a constant temperature. The pressure is inversely proportional to the volume. Okay, inverse proportional to the volume. So this is a formula for it. The pressure is inversely proportional to the volume. Okay, that's how you write that statement. The pressure is inversely proportional to the volume. Now, if we said the pressure was inversely proportional to the square of the volume, we put that. If I said that the pressure was proportional to the volume, if the pressure is proportional to the volume, then you'd say kV. Okay? So being able to write those is good. Okay, so if that's the case, the question is find the limit of P as V approaches 0 from the right. Okay? So what we're going to try to do is we're going to find the limit as V approaches 0 from the right of K over V. Okay? So we'll go to this one here and we'll graph. Okay? So what does the graph of this look like? It's this, K over X. Now, for different values of K, I'm letting K be a slider here. For different values of K, you can see the impact on the hyperbola is only the distance that it is away from the origin. Okay, that's the only thing that it does. Okay, all the rest are the same. So look at this picture. What is the limit as V approaches 0 from the right? Answer? Infinity. Okay? It's right there staring at you. That as we approach the volume, because V is the X here, as V gets closer to here, that pressure is infinity. Okay, explain this to me in just logical terms then. What does Boyle's law say as the volume gets closer and closer to 0, what happens to the pressure? Goes way up. You can imagine compressing, okay, the volume, pressing, the pressure it raises. Okay, that's the difference. Likewise, just the opposite, if V is approaching infinity, okay, if the volume is approaching infinity, okay, then your pressure is less and less and less and less. Okay? We can do both directions on that one. Okay? All right, 89, the patrol car. So the patrol car problem says that a patrol car is parked 50 feet from a long warehouse. And the revolving light on top of the car turns at a rate of 1/2 revolution per second. The rate at which the light beam moves along the wall is given by that. Okay, this is kind of a hard one to maybe understand or to try to figure out what we're looking at. So here's the deal. Here's this really long building. Okay, this is the warehouse. And then here is the car, the patrol car, and it's got a flasher thing on the top of it. Okay? What?
It came back to you.
Oh, okay. It found me?
Yeah,
Okay. It's becoming smarter.
it's evolving.
It's evolving. Okay. So the light on the patrol car is spinning. It's one of those spinning ones. Okay. So what happens here is it projects this way and then goes around and around and around like this. It's a half a revolution per second. Okay? So we're given this formula R that says this is the rate that the light appears on the wall. So picture this. If it's facing this way, that means the light, okay, is hitting here. See what I mean? So if this thing is spinning, and then it spins more, and it goes over here, and then it spins more, and it goes over here, and then it goes all the way around, then it appears over here, and here, and here, and so on. You get that? So it's like I got this here. Okay? Could just do this all day. Okay, now, so this R function gives you the rate that light is traveling on the wall at any given moment, okay, based upon the angle. So this would be 0 degrees here, or we'll say 0 degrees or 0 radians, okay. Then pi over 6, so that's like 30 degrees. So this one would be at pi over 6. And then maybe this is pi over 3. And then what we're supposed to do is figure out what R is for each one of these. Okay? So we just have to plug them in. So we'll do the first one. 50 times pi times the secant squared of pi over 6. Okay, do a little math here. 50 pi secant squared. If I put this in the bottom, does that make sense that it's a cosine squared of pi over 6? See what I did there? Put it in the bottom, it's cosine. So 50 pi, what's the cosine of pi over 6? It's one of those. Just want to warn you, I like to wait until a certain time has passed before I quiz you. Okay? I'm thinking it's about time for a unit circle quiz. Sometime soon. Unit circle quiz. Okay, cosine of pi over 6. So here's my circle. Pi over 6 is over here. Cosine is down. So it's a square root of 3 over 2. Okay. So it's a square root of 3 over 2 squared, which is 50 over pi over 3/4, which means that it's 4/3 times 50 over pi. Multiply by reciprocal. So 200 pi over 3. Okay? Now, in the theoretical world of mathematics, that is a beautiful answer. But it really doesn't mean squat. Because I don't know, I've never seen a measuring tape that's got units on, like radian values on it. Okay? So, give me a quick estimate as to what that answer is. It's roughly 200. Right? Because the pi and the 3 would cancel each other out. So it's a little bit. So I can say this is around 200 something, but even 200 is probably just good for common sense. That's 200 feet per second. That's how fast that thing is moving. Okay? If you could put a... It's not the thing. If you could put a speedometer on this thing, it would be moving at 200 feet per second as it's going to the right. Okay? All right, let's do pi over 3. But before I do pi over 3, is that answer going to be bigger or smaller than 200? Is this going to be moving faster or slower when it reaches this point? Okay, versus this point. Remember, we're putting a speedometer on the light as it's traveling down that wall. Is it going faster or slower? Should be going faster. So this number should be bigger. So here we go. 50 pi times secant squared pi over 3. 50 pi cosine squared pi over 3. We know that one's now 1/4, so it's 50 pi, well, 1/2, but then we're going to square it. 50 pi over 1/4. So look at this. This is 200 pi feet per second. We just proved that when the light is hitting the pi over 3, it's going a lot faster, about 3 times as fast. Okay, so it's about 600 feet per second. Okay, so knowing that and that, how fast is it going as theta approaches pi over 2? How fast is this light beam traveling on that wall? As theta goes to pi over 2. Where's pi over 2? In this case, it's this way if we consider this as 0, right? So obviously, it's not hitting the wall at pi over 2. But what do you think the answer is for how fast it was going as we approach pi over 2? Infinity. Okay? So the answer to this is infinity, which is kind of really fast. Okay? You can't actually follow the light beam that far because you would need a wall that's infinitely long. And that would take a long time to build. And then we'd have a problem because we're on this globe, and the globe curves, and then we'd have to go out into space and build this wall. And yeah.
So in the problem, the A, B, and C, that is the different speeds?
Yes, these are the different speeds. It's how fast. So if I do this again, if I were to move around at a constant distance, is the dot always moving the same rate? Well, that's weird because I'm turning at exactly the same rate. But do you see that as I'm like in here? This is like slow-mo now. See? And then it speeds up. Does it make sense that in here it moves slower? And then as soon as I get towards the edges of the wall, that's where it's moving the fastest. That's what this is. It's how fast the light beam is traveling on the wall. Okay?
Makes sense when you do that a little bit.
That's why I do it. Okay, and the last one was number 60. It's all about illegal drugs. So there's always this problem in government where they say drugs are bad, we should take them off the streets. Okay? But everything costs something. Okay? And so this is actually a formula that computes the cost of eliminating a certain percentage of the drugs that are on the street. Okay? X is the percent of drugs that they're seizing, and C is the cost. Okay? So they said, find the cost for removing 25% of the drugs. Okay, so let's do that. So the cost is C of 25. Okay? So it's 528 times 25 divided by 100 minus 25. Okay, I don't know what that answer is. Anybody got that answer? 176? Just like that? Is this in like thousands? Millions? Okay. So so that's $176 million to remove 25% of the drugs. Okay? Then they asked, what was it, like 50%? So if it's 50%, okay, here we go. What's C of 50? More or less, answer? It's going to be more. Okay, so it's 528 million. Right? Is that what you said? Okay. So the more drugs you try to seize, the more it costs. Okay? Duh. But does it go up in a linear fashion? How much does it cost to remove 100% of the drugs? It's 528 times 100 divided by 0. You guys had an actual answer? Okay, I've got the picture up here. So let's take a look at it. Yeah, come here. So here is the graph of the illegal drug cost to remove percent of the drugs. Hey, that looks linear to me. So look at 25%. 25%. Where's 25? What was that? 176? So here it is. 25% is 176 million. See that? Does it get any, does it cost more as you go up? Uh-oh. Asymptote. See, it looked linear at first when we were close up to it, but it's clearly not. It's actually a hyperbola. And where is the asymptote? At x equals 100. Okay? So this is saying, how much would it cost? It would cost an infinite amount of money. Okay? To remove every ounce of illegal drug is an unrealistic expectation. Because it's just cost too much. Unless you just make them all legal, then you've just removed all the illegal drugs.
Yeah.
What did you learn today? Mr. Johnson legalize all drugs.
No, I didn't say that. I just said it's cold. Yeah.
Documented.
No.
I do not support making drugs legal.
Did you hear me? Yeah. That's right. Watch out for this one. Okay. You have an assignment. Due. No, this was the last assignment. And so we'll go over those questions tomorrow. But also, this is now the practice exam. Okay? So I'm going to hand this out right now. Come and get one. And we'll go over it tomorrow.
I'm gonna hand this out. Sure.
I'm just really upset about Bailey still.
chapter summaries. Do you want us to like make sure that we have like basically everything it says in there, or because there was like a whole section that I didn't understand what it was saying because it was using weird variables and stuff.
Yeah.
Should I put that in my notes even if I don't personally understand it? Or
Yeah,
what?
that particular one, I'm going to talk to the whole group about.
Okay.
So, but put it in there anyway because it's in the book. Because that's the difference between the chapter summary and then what I talk about.